Okay, guys, so as I put up on Google Classroom earlier today, all right, today we're just going to have kind of a short little mini um, kind of lesson, just piggybacking off of what we did yesterday. Yesterday we worked a lot with using, our basic trigonometric identities. All right, we did a lot of simplifying, we did some factoring, we did quite a few different things with them. All right, today we're going to expand on that a little bit, and we're just going to be doing what's called verifying trig identities. All right. Basically, a verification is very similar to a simplification, except with a verification, you have a goal that you are supposed to get to. All right. We're still going to be heavily relying on our identities that we went over again yesterday, but we've been using them pretty consistently now for the last, month and a half or 2 months, really. So, of course, all of our reciprocal identities, all right, our quotient identities, all right, our Pythagorean identities, all right. These are the ones that are used most heavily. All those three: reciprocal, quotient, Pythagorean. All right. And then some of the lesser used ones, the cofunction identities, and the even odd identities. We went over all of those again yesterday. Like I said, that was certainly not the first time we had gone over them, but you will definitely want all of those, all right, in front of you as you do these. If you don't, you're not going to be able to do them. I mean, unless somehow magically you have them all thoroughly memorized by heart at this point, which I highly doubt for most of you. All right, you're going to have those in front of you. All right, so let's do a couple of examples. All right, and on the worksheet that I just handed out with you, we'll first look at number one. All right, so number one says secant of x minus tan of x times sine of x is equal to 1 over secant x. Okay, so the idea of a verification is unlike a simplification, they give you the answer. They say this thing equals this thing, all right? Basically, a verification is show me how to do it, right? Show me how you get from here to here, right? As mentioned yesterday, one of the rule of thumbs for trigonometric simplifications and verifications is to put things in terms of sine and cosine. Right now, although it will always work, sometimes that does make it a little bit more complicated than it needs to be. So you may want to take a cursory glance over the identities first and see if any of them kind of stand out to you as far as that's definitely going to be helping. And if it's one that, specifically, typically the Pythagorean identities, the 1 plus tan squared theta is equal to secant squared theta, and the 1 plus cotan squared theta is equal to cosecant squared theta. Those ones typically are the ones that will typically jump out at you, right? But anyway, let's go ahead and just put things in terms of sine and cosine first. All right, so secant x is 1 over cosine of x, just one of our reciprocal identities. All right, minus tangent of x is equal to sine of x over cosine of x. That is one of our quotient identities. And of course, sine of x is already in terms of sine, so we don't have to do anything with that. All right. If it makes you feel better, you can put this over 1 just so that everything is nice and neat in the form of fractions. Okay, so I'm going to leave this 1 over cosine x for the time being. All right. And I'm going to go ahead and multiply these two fractions here. So just multiply across the top, multiply across the bottom. So of course, sine x times sine x is sine squared x. And cosine x times 1 is, of course, cosine x. All right, well now, both of these fractions have a common denominator. So I can go ahead and combine them into one fraction. So this will be 1 minus sine squared x over cosine x. All right, now this 1 minus sine squared x should kind of jump out to us whenever we have a trig function squared and a 1, all right? Really, anytime we just have a trig function squared, but absolutely when there's a 1 in there also, we're definitely going to be using one of our Pythagorean identities, right? This one has sine squared. So this is off to the side. This doesn't have to be work within the main body of the problem, all right? But our Pythagorean theorem says that sine squared theta plus cosine squared theta is equal to 1. All right, now, of course, when I write these down, I typically write thetas. Some of the problems have x's or y's or u's, right? It doesn't matter what it is, okay? All it is a placeholder for some angle that we don't know, all right? It doesn't matter if it's theta, x, y, u, s, t, dollar sign, smiley face, unicorn, unicorn jumping over a rainbow, right? It doesn't matter what you pick there. You can choose whatever you want. It's simply a placeholder, all right? So here we have this 1 minus sine squared x. All right, so I want to manipulate this identity so that I have 1 minus sine squared on one side of the equation. All right, well, that's really easy. All I have to do is subtract sine squared theta from both sides. All right, and from here, all right, of course, our sine squareds cancel here. So now we have cosine squared theta is equal to 1 minus sine squared theta. In mathematics, whenever two things are equal to each other, they are completely interchangeable. Right? That means wherever I see 1 minus sine squared theta, I can replace it with a cosine squared theta. Or in this case, wherever I see 1 minus sine squared x, I can replace it with a cosine squared x. And of course, that's still over cosine x. Well, we talked about this a lot yesterday. What happens when we have a cosine squared x on top and a cosine x on bottom? Yeah, right. Cosine squared x is really cosine x times cosine x. So one of these cosine x's up top cancels with the one on the bottom, and we are just left with cosine x, right? Well, we're trying to get to 1 over secant x here. Well, that's really easy. Cosine of x, according to one of our reciprocal identities, is 1 over secant x. Okay, we got to exactly where it told us we're supposed to get to, so we have verified that trigonometric identity. Right? So in some ways, verifications can be easier than simplifications. In some ways, they can be harder. Right? It's easier in the sense that you know what the answer is, you know what you're trying to get to. Okay? It can be harder in the sense that a lot of times when you're just doing simplifications, since you don't have some specific aim and goal, right, you just kind of play around with it and eventually you get it, right? So there's a lot more freedom in a simplification, but there's a lot more direction in a verification. All right, so let's go ahead and look at one or two more. All right, let's flip around and look at 9. All right, so we have the quantity of sine theta plus cosine theta squared plus the quantity of sine theta minus cosine theta squared, and that is supposed to equal 2. Okay. Well, whenever we square something, right, that's really just multiplying it by itself. Okay, so this is really sine theta plus cosine theta times sine theta plus cosine theta. So if you were to go ahead and distribute all that out, or FOIL it if you're one of those people, all right, then when I distributed sine theta plus cosine theta to itself, I would get sine squared theta plus sine theta, oh, son of a biscuit, plus sine theta times cosine theta plus cosine theta times sine theta plus cosine squared theta. All right. Now, when I do the same thing with sine theta minus cosine theta squared, right? So now I'm distributing sine theta minus cosine theta to itself. I will get sine squared theta again, minus sine theta cosine theta, minus cosine theta sine theta, plus cosine squared theta. So a lot going on there, right? But it's just simple expansion. All right, well, here I have a plus sine theta cosine theta. Here I have a minus sine theta cosine theta. What happens there? Yeah, cancel each other out. All right, similarly, I have a plus cosine theta sine theta here and a minus cosine theta sine theta here. So they will also cancel each other out. All right, so now I'm simply left with sine squared theta plus cosine squared theta plus sine squared theta plus cosine squared theta. All right, well, sine squared theta plus cosine squared theta is one of our Pythagorean theorems, or Pythagorean identities, rather. All right, so sine squared theta plus cosine squared theta is equal to what? 1. So this is equal to 1, and this is equal to 1. What's 1 plus 1? 2. Yay. Is that what we were supposed to get? Absolutely. So we have successfully verified. All right, as I mentioned yesterday, all right, there's most of the time a lot more than just one way to do these. Okay, so if you ask your neighbor how to do something and they're doing it totally different than you are, does not mean you're wrong. All right, 3 or 4 students could be working on the exact same verification and be doing it 3 or 4 completely different ways and all be correct. It's fine. All right. So go ahead and look at this worksheet and pick one that you think might give you issues, and I'm more than happy to work it out for you. Any suggestions? If I recall from last block, 13 was tricky. 3 was a little tricky. Slacker. Gotta leave one of them for you. You want 3 or 13 then? Okay, 13, because that's what side I'm on. So we'll do 13. All right, so 13 we have cosine of x plus 1 over sine cubed x is equal to cosecant x over 1 minus cosine x. All right. Now, technically, you can work with either side and make it look like the other one. In a case like this, it wouldn't really matter. But it's oftentimes easier to take more complex, trigonometric expressions and simplify them down than it is to take a very simple expression and expand it out, because there's always a million different ways you can expand it out, whereas there's only so many different ways that you can simplify it down. Okay, so just for future reference. Okay, now I know that I'm dealing with a cosecant here, and I have a sine cubed in the denominator. Okay, so what I'm going to go ahead and do, is just change this to sine x times sine squared x. Do we all agree that that is still sine cubed x? All right, and just for show, I'm going to go ahead and multiply this whole numerator by 1. Okay, well now I can go ahead and break the two parts of the numerator and the two factors in the denominator apart, right? And I can kind of say, okay, well, this is really the same thing as 1 over sine x times cosine x plus 1 over sine squared x. Do we agree again that if we just multiplied across the top and multiplied across the bottom that we would still end up here? Okay. Well, 1 over sine x, using our reciprocal identity, is cosecant x. All right, so I'm good. Here, I have my numerator kind of done for me. All right. Now again, I see sine squared x. What should that kind of trigger in my thought process? Pythagorean identities, all right? And that specific Pythagorean identity that involves sine squared is sine squared theta plus cosine squared theta is equal to 1. All right, now I want one side of my equation, of my identity here, to just be sine squared theta. Okay, well, let's just subtract cosine squared theta from both sides. All right, again, whenever two things are equal in mathematics, they are completely interchangeable. So where I see this sine squared x, I'm going to be allowed to replace it with 1 minus cosine squared x. So I'm going to go ahead and do that. So I have cosine x plus 1 up top and 1 minus cosine squared x on the bottom. Okay, now, yesterday we did significant work factoring trigonometric expressions. Okay, well, 1 minus cosine squared x is a difference of perfect squares. Right? Remember, we used some u substitution yesterday and just said, okay, well, let's let cosine x equal u. So cosine squared x equals u squared and all of that. All right, of course, you can feel free to use all of that. All right, but for showing work and not using a million steps, all right, I'm just going to go ahead and factor it. So this stays the same. My numerator stays the same here. All right, and factoring a difference of perfect squares, this is going to be 1 plus cosine x times 1 minus, cosine x. Right now, addition is commutative, which means the order doesn't matter, right? 3 plus 7 is the same as 7 plus 3, all right? So cosine x plus 1 is the same as 1 plus cosine x. So what happens there? They cross them out. Now we do have to be careful because about half of you in here like to just pretend like now that these cancel, that this thing magically comes up to the numerator. All right, when everything in the numerator cancels, what has to be there as a placeholder? A 1. All right, so that whole thing cancels, and we just have a 1 over here. Okay, so now, just so that we can see some more of what I was doing up here, all right, I'm going to go ahead and rewrite this. So I still have my cosecant x, all right, and now I'm multiplying this by 1 over 1 minus cosine x. Oh, okay, well, if I think of this as over 1 and I just multiply fractions, multiply across the top, multiply across the bottom, I get cosecant of x over 1 minus cosine of x. What were we trying to get to? That, right? So I got there. Bada bing, it's been verified. All right, again, guys, this is something that is a little bit different than most things in mathematics, right? Typically in mathematics, you can follow some algorithm that says if you do this, then you do this, then you do this, then you do this, right? You're always going to get to the correct answer, right? These aren't quite as cut and dry, right? These are more like puzzles, right? Where you kind of have to take out puzzle pieces and using trig identities, rearrange them and then try to stick them back in and see if they fit. All right. And they really just take practice and experience. Right. Once you do enough of them, you'll kind of start to see kind of little tricks and ideas that will kind of work when you get into certain situations. All right. But it does take practice. All right. So for the rest of the day today, I just want you to practice with the rest of the problems on that worksheet. Yes, sir? 3. Mm-hmm. Yep. Okay. So, sure, I suppose. Slackers. All right. But this will be the last one I do for you. Okay. So 3 says secant theta sine theta, all right, over tan theta plus cotan theta. All right, and that is supposed to equal sine squared theta. Okay, well, yesterday, one of the kind of rule of thumbs that if you ever get stuck or don't see anything obvious is to put everything in terms of sine and cosine. Okay, so secant, I'm going to change to 1 over cosine. All right, sine is already good. All right, over tangent is sine of theta over cosine of theta. Plus cotangent is cosine of theta over sine of theta. Okay, so I'm going to just go ahead and combine my numerator here, just multiply across, and that gives me sine of theta over cosine of theta. Right, now my denominator is going to be a little tricky. I'm adding fractions here. All right, if I wanted to add 2/3 plus 4/7, what would I have to do? Get a common denominator. What would that common denominator be? 21. How did we get that? Yeah, multiply 7 and 3. Okay. Well, here it's the same concept. Just because I'm dealing with trigonometric expressions, it doesn't mean that math changes, right? That's the great thing about math is it never changes, right? It gets more complicated, but it never changes, all right? So I'm going to have to get a common denominator before I can add these two fractions. Well, it's not like numbers where we've just kind of been trained to see. So let's just use what we did here. We just multiplied them together, right? So my new common denominator here is going to be sine theta times cosine theta. Okay, well, how do I get this cosine theta to be that? Well, I have to multiply it by sine. Well, whatever in a fraction, to keep it the same, whatever I do to the denominator, I also have to do to the numerator. Right? And since the whole purpose of that is sine of theta over sine of theta is simply 1, multiplying something by 1 does not change it. All right? So similarly here, now I need my denominator to again be sine theta times cosine theta. So I have to multiply this denominator by cosine theta, which means I also have to do the same thing to the numerator. Right? So now this piece is going to be sine squared theta over sine theta cosine theta. Right? And this second piece over here will be cosine squared theta over sine theta cosine theta. Well, now they have a common denominator, right? I can go ahead and combine them if I wanted. So it would be sine squared theta plus cosine squared theta over sine theta cosine theta. What is sine squared theta plus cosine squared theta? 1, right? So really, this whole thing now simplifies to my numerator stays the same. Sine theta over cosine theta. Right? But my denominator now becomes 1 over sine theta cosine theta. Well, when we did a fraction divided by a fraction in middle school, what was our little trick? Keep, change, flip. So that's what I'm going to do here. All right, I'm going to keep my numerator, sine theta over cosine theta. I'm going to change my division to multiplication, and I'm going to flip my denominator. So now it's sine theta cosine theta over 1. What happens to this cosine theta in the denominator and the 1 in the numerator? They cancel. What is sine times sine? Bam. That's what we were supposed to get to. We have verified. All right, so some of them are very complicated. Some of them are very simple. Right? Number 2, for instance, is literally 2 steps. You only like if you kind of see the right things to do, it's just bang bang. All right. So I will go ahead and end this video